this video I again look at error detection and correction. Just to reiterate, now the objective of error detection and correction, in one sense it's a bit opposite, but also the same as that of data compression in another sense. So you have L dash bits here, you wish to code this in a slightly larger value L bits, so that when if any error occurs in any of these L bits, if these L dash bits are coded in L bits and transmitted across, and L bits are received, exactly L bits, I do not assume that more or less than L bits are received, and some errors occurs in any of these L bits, the value as represented by the code does not change the value of the information. The information is L dash bits, but the code is L slightly larger than L bits. So in that sense, these L bits are immune to certain amount of changes or flips in the bits of those L dash bits. Okay. To that end, now this form of error detection and correction can be performed at two levels. One is at the physical level, which is the router level, where there is one actual router which is transmitting, assuming that it can transmit across different links with different capacities and different error rates, meaning if this is one physical vertex here which represents a router, and this is another router here, and there is a physical link connecting these two routers which has a certain error rate. When I say error rate E, if E is large, actually the number of errors is less. This means if I say error rate is E here, I assume it means that if you transmit E bits across this link, you might expect an error of 1 bit in that. That is what I mean by error bit. If the error rate is higher, it means the number of errors that occur is lesser. Okay. So I am assuming this as the basic model here. So this is for the physical error checking and correction. This method can be one possible approach to handle error. If you have two vertices here connected by a link with an error rate E, this is one way of performing error detection and correction across that particular link. Okay, so again we have two nodes here connected by a link and an error rate E. This is the edge connecting these two vertices. On an average, if E bits occur and L dash bits are L bits are transmitted across this link, which has an error rate of E, that means we might expect about 2L by E errors. Okay, right? It will be L by E, but that being the average case, I double it and make it 2L by E. Okay, let D equal to L by E. Clearly, in order to transmit L dash bits as L slightly greater than L dash bits across the link or H, we require the cardinality of the largest subset of the superset of 2 power L elements. So there are 2 power L bits are being transmitted. It's the superset of 2 power L elements, out of which we require the cardinality of the largest subset of the superset of which, where each element in the subset differs from every other element in the subset in D or more bit positions, to be not less than 2 power L dash. It means what? 2 power L dash by LCD equal to 2 power L by LC 2L by E must be greater than or equal to 2 power L dash. Only then we can account for or accommodate 2L by E errors, D equal to 2L by E errors. Because each value we have chosen is able to tolerate up to 2L by E errors. Therefore, in other words, we require 2L by LC 2L by E greater than or equal to 2 power L dash. Now, if NCR requires NCR, if NCR combinatorially, to code NCR requires R binary log Lg of n by r bits. Okay, assuming that, this means we require 2 power L by 2 power 2L by E binary log of L by 2L by E must be greater than or equal to 2 power L dash. Okay. Therefore, we have 2 power L minus 2L by E log of E by 2 greater than or equal to 2 power L dash. Okay, that means we require, just equating the exponents, L times E minus 2 log E by 2 by E must be greater than or equal to 2 power L dash. Which gives us L must be greater than or equal to L dash into E by E minus 2 times log binary log of E by 2. Okay. It does not increase by too much. If the error rate is, it means for large values of E, meaning you can transmit more number of bits with fewer number of errors, that is, the strength of the link is more, meaning the amount of errors that occurs across that is less, then the correction, the length required to code for the correction and make up for possible errors in it that occur during transmission will be less only. Okay. The question now becomes, given a binary string of length L, what is the cardinality of the largest subset of the superset of 2 power L elements where each element in the subset differs from every other element in the subset in at least d bit positions? In other words, we wish to code those 2 power L dash as some 2 power L dash subset of the 2 power L elements, such that each element in this set differs from every other elements in d or more bit positions. Meaning, so if at least d or lesser errors occurs, the value does not change as coded by this, because you know that it is this can occur from this only from making. Okay. So that is the objective here. This is a question where figuring out a combinatorial formula for answering it may not be as easy as trying to devise an algorithm for generating such a set to answer the question. And the following algorithm attempts to do just that. In other words, for a given value of L dash, we assume a tentative initial value of L is equal to ceiling of L dash E by E minus 2 times binary log of E by 2. This, okay, we assume this as a tentative initial value of L. Consider the superset of L elements. Superset of 2 power L elements, which is equal to, say, U. Okay. Now let S be the desired set to be constructed from the elements of U such that each element in S differs from every other element in S in at least d or more bit positions. Okay. Initially, S is the desired set. Okay. Initially, S is equal to the null set phi. Okay. We begin by choosing an element X belongs to U such that the cardinality of the set D, which is the set of all elements in U which differ from X in less than D positions, D bit positions, is fairly minimal or small. In other words, you have the set U here. Now from this set U of 2 power L elements, I will select an element X such that, now for this X, element X chosen, there will be the set of all elements which differ from X in less than D positions, less than or in less than D positions, right? So that set, let that set be D. And if I will choose an element X, you choose an element X such that the value of the cardinality of D is as small as possible, fairly small. You might choose different values of 1 bits once occurring. Different typical candidates say for different possible values of 1 R, ones that can occur, NCR, up to L different choices, random ones, rough ones, which are fairly uniformly distributed across, and choose one for which this cardinality is minimum. The elements which differ from that is the smallest. Okay? Now we include that element in S. Therefore, you have S, you set S to S union the chosen element X, binary string of length L, and you remove the set D from U. That is, you eliminate all those elements which differ from X by less than D positions out of the universe from which you have selected. So you set U to U minus D. Now you repeat the process. Now you have a new value of U, and this value which is slightly reduced by all those elements which can possibly conflict from this. Okay? So now what you do is you choose another element X, and so on, keep doing it, which, and at each stage for that you eliminate the corresponding set D from U. Okay? Then you will be left with the set finally until U is equal to the null set, U becomes empty. Now the cardinality of S will give you the size of roughly the size of close to the maximum number of for a given length L. What is the maximum and difference D, error rate, that is what is the size of the cardinality of the set which can account for up to D or more errors. Okay, D or more errors. So this will give you the cardinality of that set, roughly very close to that. At each stage you choose always minimal. Here it will give you the least possible value. Now if this cardinality of the set S must be greater than or equal to 2 power L dash. Now for the initial tentative value of L we have chosen, we start off with that value and we find the cardinality of this set S is greater than or equal, we stop. Otherwise we have to increase the value of L. By how much? We can either simply increment it L to L plus 1, or increase it by how much does the cardinality lesser than 2 power L dash. We note that and try to tentatively increase it by more. And if need be, when we do attain a value, we could try reducing or decreasing it by decrementing it to come to a certain reasonable optimal value where it can handle. So this form of error detection and correction is ideally suited for performing error detection and correction at the router level or the node level. Okay, so this kind of algorithm, it will be slightly computation intensive, but it is still right. Periodically the error rate across rings can be determined. The other error detection and correction technique that we I dealt with is ideally suited across for performing it at the logical level, at the operating system level or the computer user level or programmer level. If you are transmitting a file across, you don't care for what the kind of error detection is, such as this, it's performed at the router level. But you do care for the integrity of the file that is received at the other end to be the same as match that of what was sent across. Then you might try adopting something like that, which I dealt with, which involved combinatorial coding or generating permutation and sorting algorithm, all that. One of those techniques like that can be adopted at the user level or the logical level. At the physical node level or the router level, techniques like these can be adopted. Now, the only thing to note here is if the error rate is E is more, it means fewer number of errors occur. E bits can be transmitted across fairly readily.